Welcome everyone to the week 1 tutorial session of Galois theory MA70. Today we'll discuss sample questions related to week 1. Basically I'll discuss non-blue non-star questions of week 1 tutorial. So let's begin. Okay. Okay. I think this is visible, this font. I hope so. Yeah. Okay. Okay. Also, if you have any doubt in any definition, I can write it down here, so you can ask that also. So let's start. Let R be a commutative ring. And you fix some points, let's say A and B, for at least for first part. A and B, there are 2 points from the ring, so elements of the ring. Firstly, okay, so ring, okay, what is a ring? Can anyone tell me? Of course, I can write it down if you need, if you want me to.
It's a tuple with an abelian with 2 operations and 1 set, and it has to satisfy some axioms like all abelian group axioms. And regarding multiplication, there should be unity and distributive laws should be satisfied. Yeah.
Exactly. Yeah. Very good. Yeah. So exactly as you said. So with respect to addition, this is a abelian group. That means it satisfies 5 properties. It is closure under addition. It is associative under addition. It has identity element, and usually we will write that identity element to be 0. Element to be 0, and identity element with respect to addition. Okay, so with respect to addition, you have identity element and it has inverses with respect to addition. That is like if, and we usually denote if A belongs to R, then minus A will be the inverse of A in R. So inverses are also there of A. Okay, and it is commutative with respect to addition. So if A and B belongs to R, then AB is equal to so with respect to addition, as I said, so A plus B is equal to B plus A. So, and with respect to multiplication, it is a monoid. That means it has it is closure. So with respect to multiplication, A dot B, it is also there if A and B belongs to R. Second, it has identity, which we will say 1 to be the identity, and we usually take all the rings to be with identity. Of course, there are rings with no identity element, but we will not consider that in the course. So it is just identity is always there in a ring. One belongs to R, and of course associativity is there. A dot B dot C is equal to A dot B dot C. Okay, for all A B C belongs to R, and we have commutativity with respect to multiplication. That means A dot B is equal to B dot A for all A B belongs to R. And there is extra property relation between this addition and multiplication, which is distributivity. That is A dot B plus A, this is for all A, B, C belongs to R. So we have these properties. Okay, so this is a ring. Now so we will consider all the rings to be with unity, and it is commutative. Okay, in this course. So commutative ring, R is a commutative ring and A and B belongs to R. So it has been asked that show that there exists a unique ring homomorphism FAB Rx to Rx such that FAB over C is equal to C, like FAB at any point of the ring R, it is exactly the same element. So basically it fixes that element, fixes the elements of R, and FAB, so evaluation of FAB at X is equal to AX plus B. So it maps AX to AX plus B. So A and X, we started with some elements A and X. Now we are say it has been asked whether you can construct a ring homomorphism using A and B with such as it fixes every element of R, and it maps X to AX plus B. Can you construct some ring homomorphism like that? And moreover, it is unique in that sense. So it is unique with such properties. So two things uh, need to be shown. So first, existence. So I'm just proving first part right now. Show that there exists a unique ring homomorphism. So okay, so so basically for existence, what can we do? Can anyone tell me? So we need to construct some phi. Right now we will write phi. Okay, so I can. Okay, so we need to construct some phi Rx to Rx such that these two property holds, like phi of C is equal to C for all C belongs to R, and phi of X is equal to AX plus B for not for all, it's just, so it maps X to AX plus B. So two properties we require to define phi, so to say. So I'm just writing phi right now because I don't know if it is unique or not. Until I'll prove it, I cannot write FAB because it is kind of unique in that sense, because the notation says that. So can you construct some phi like this, or can you tell me what I should define it? So I'm removing this because I want these two properties anyway. So let phi phi be a map defined by, so how should I define? So there is some fx. uh, what is your intuition for this? What your heuristic says? Yeah, we
So
should.
shall we define
Hmm.
phi of fx as ax plus b,
uh,
or c if c is
uh,
uh,
okay, you want phi
just
of.
take a so give a multiple definition that. So anyway, f is defined by a and b, the parameters a and b.
Exactly.
So phi of f is equal to ax plus b if
Okay,
f is not a constant.
if f is not a constant,
F
so
is not
okay, let me
means
write it down what you are saying. So you are saying phi of fx. Okay, I'll write symbol capital X because in the next question, at least sir has used it. Phi of fx, what you are saying, it is ax plus b
ax plus b
if uh,
if uh,
Ma'am, it is f of ax plus b. Can you, if we prove that, it is over, I think. Yeah.
okay, yeah, so one option you said, okay, one second. So one option is phi of fx maps to f ax plus b. So okay, I cannot see the name, so I don't know who is speaking, but yeah, you can tell me your name also.
Nageshwarao, ma'am.
Sorry.
Nageshwarao, ma'am.
Okay. Yeah.
Yeah.
Yeah, Nageshwarao. And earlier, what was who was saying ax plus b
yeah,
if, yeah, yeah.
I'm Dinesh.
Oh, Dinesh. Okay, yeah. So you were saying ax plus b if.
Uh,
Yeah. So let's say Nageshwar. Rao, he said phi of fx, define phi of fx to be phi of ax plus b. This is one, so I'll call Dinesh one. Yeah, so ax plus b, if f is non-constant, right? You said that?
Yes.
Okay,
Yes.
f is non-constant. Okay.
And define it to be the constant if f is constant.
Which constant I should take?
Means for any c in R,
Mm-hmm.
if fx is equal to c for all, I
Okay, you
mean,
are
then
saying
you just
let's
keep the
say
constant.
c if fx is equal to c, which is a constant.
Yeah.
Just the constant term is there in fx. Okay, so if fx is constant, then let's say c, and if f has, let's say, degree 1 or
Yes.
bigger, you define it to be ax plus b. Okay, let's
Yes.
see if it works or not. Okay, okay, you okay. So, of course, for phi of x, it works because it is non-constant and it maps x to ax plus b. And of course, this is equal to c for all c belongs to R. Yeah, both properties are satisfied, but you also need to make sure that this is a ring homomorphism because we need to define a ring
Yes.
homomorphism, right? So let's
So it
see if
doesn't.
this is a ring homomorphism or not. So for ring homomorphism, what we all need to prove, I can switch colors. Yeah, ring homomorphism. What all properties we need to check?
First, it's an abelian group homomorphism.
Sorry, come again.
First, it should be an abelian group homomorphism.
Okay, so you mean group homomorphism. That's, we can
Yeah.
write the property also, f of, or maybe I should write phi from, I'll just define some different, so let's say R to S, or S to, I don't know, maybe K. Okay, some phi is a ring homomorphism if phi of A, phi of s plus t is equal to phi of s plus phi of t for all st belongs to s, right? So this is from group homomorphism with respect to addition. Second, what we want, phi of s into t is equal to phi of s dot phi of t. Of course, this addition is coming, so this addition is with respect to s, this addition is with respect to k. Okay, and this multiplication is with respect to s, and this multiplication is with respect to k. Of course, the multiplication will be defined in that ring only. So phi of s into phi of t is only defined in the ring k. So these are two rings. Okay, is that clear for everyone? You can ask me if you have any doubt, because right now we are basically introducing prerequisite for this course. So uh, it will be good if you understand these things because it will come again and again in the course. So if you have any doubt, just unmute and let me know. Okay, so phi of 1s is equal to 1 of, so it maps multiplicative identity to the multiplicative identity. So again, we will not write this s here, k, these suffixes for the addition and multiplication, because we can say that this is understood from because it will be defined only in that ring only. So we will not write it again and again. So so these three properties should be satisfied. So this is multiplicative identity in the ring R, in the ring S. This is multiplicative identity identities in respective rings. Okay, so these three properties we need to make sure that it satisfies, right? So let's see what Dinesh definition says. So okay, so if this is non-constant, this maps to ax plus b. So what we have to see, so let's say this one. So phi of s plus t. Of course, this is verified because one is going to one, because both the rings we are considering is R of x. Also, is the definition clear of R of x? This is a polynomial ring, fx, okay, fx, where f is a polynomial with coefficients in R. Okay, this is that ring, and you can easily check that this is a ring. Now phi of phi of s plus t should be phi of s plus phi of t in the same ring, because domain and codomain are same in this scenario. So okay, so if you take so what can you take? Can you tell me, Dinesh, if this could work or not, or which example can you try to check? So,
Yeah, S is a non-constant and T is a constant. I think it doesn't work.
it doesn't work, right? So yeah, if you take yeah, exactly as you said, if you take s to be x, and let's say t is 1, I can write 1 as to be the identity, then this is equal to ax plus b. But on the right hand side, it is phi of s, that is phi of x plus phi of 1, which is ax plus b plus 1. So this is increasing, like this is not equal.
Yeah.
Yeah, but it is a good start, of course. So what can we modify here? So what we really require, let's see, because we don't want to just jump to let's define the map and we do it. So we can actually see which one will could work. So what you really need, the three properties you require. So one property is definitely satisfied when you fix constants to go to constants. That means for all C belongs to R, if you fix that, then identity will map to identity for sure. So there is no problem there. But when you take any polynomial, let's say fx plus, okay, as I said, I'll use capital F. So I'm using f and gx. Okay, I should write properly. For let fx and gx belongs to Rx. So what we really require, phi of fx plus gx should be equal to phi of fx plus phi of gx, right? We need this. And okay, yeah. Also, okay, so phi of and the other property you want, phi of fx into phi of gx is equal to phi of fx into phi of gx. These two properties you need now. Now what you can do in this one, what is happening actually? So you want now okay, how phi of fx should split in your sense? So fx is what? Fx is like a0 plus a1x. This is some kind of a polynomial. This is a polynomial. So there will be some degree, and let's say n is that degree. That means an is non-zero. Okay, this is your fx. So you have considered the polynomial. So polynomials are like sequence of numbers, of which only finitely many of them are zero. Only finitely many of them are non-zero. It's like that, the definition for a polynomial. So yeah, an is not equal to 0. So this is your fx. Now what do you want? You want phi should this is addition in the ring, right? Because this is a element of Rx, right? A0 is in R, so it is in Rx, right? This is a constant polynomial. This is also a polynomial. This is also a polynomial. So all these coefficients are polynomial in Rx. So what do you want? Phi should split on this. So split means this property should satisfy. phi should phi of one polynomial, phi of sum of the polynomials is equal to phi of um, uh, sum of phi of the polynomial. So what I mean to say, I want this property to be satisfied. So what I really want, I want this should be equal to phi of a0 plus phi of a1x plus up to and so on phi of an x raised to power n. I want this, right? I mean, split in the sense like it can split with respect to addition because of this property, because I want phi to be a ring homomorphism, so I am trying to construct it. So now a0 is what? A0 is a constant. This coefficients are coming from the ring R. So and what we require as a property, that it should be constant on the ring element. So that means phi of a0 should be a0, right? Plus now just okay. Although I can let's split more here. So phi of a1 into x is what? Again there is some property coming into picture. This multiplication and multiplication of rx is same. So a1 is an element of rx, x is an element of rx. These are some kind of two polynomials in rx. Now from the second property, what we know, that it should phi should split in here. So that means phi of a1x should be phi of a1 into phi of x. That means what we want, this, and up to and so on. Now here also phi of an x raised to power n, what it should be, phi of an phi of x raised to power n. Moreover, we can split more. What is this? X into x into x into x. So you can again apply this multiplication ring homomorphism requirement. So I'm doing it recursively. So we have this property for two elements multiplication. I can recursively do it for three. Like if I have fgx, I'll first do it for fg and then h, and because associativity holds here, so I can do that. So this will be equal to phi of an into phi of x raised to power n, right? So this will be this. So as I said, this is my requirement. So and again phi of a0 is a0 because I want phi to fix elements of ring R. Phi of a1 is a1 because this is an element of R, and this is, and what is phi of x? What we want x to map to?
ax plus b.
Exactly, ax plus b, and so on. Phi of an is an, and phi of x is ax plus b raised to power n. Can you tell me what I can write it to be in terms of f?
F of ax plus b.
Exactly. So you can think of like you replaced x to be ax plus b, like because you can see at the place of x, ax plus b is coming. So if you see, we constructed from two requirements, that is like it maps it fixes elements of R and it maps x to ax plus b, and assuming that this is a ring homomorphism, it turns out that phi of fx should map to phi of ax plus b. So so in terms of existence, but I have constructed like this, but you can make sure that this is a ring homomorphism because I use some properties of ring homomorphism, but like because it looks uniquely, but still it remains to verify that this is a ring homomorphism. So what we can do, so at this place, as Nageshwar Rao said, phi of fx, let's map it to f ax plus b. Okay, so in terms of existence, So you define phi to be Rx to Rx. Let phi be a map defined by uh, phi of fx is equal to f ax plus b. So a and b are fixed from the beginning right now. So this is true. This is for all fx. Sorry, for all fx belongs to Rx. So we have defined on every element of Rx now, and so as an exercise, I can say, because I kind of proved it, but you can. Okay, I can change color of this. Verify that phi is a ring homomorphism. So again, what you need to check, homomorphism. Okay, and you can see that phi of R is equal to R for all R belongs to the ring R, and phi of X. So if you take fx to be X, then what it will be? F is just constant. Sorry, not constant. Fx is X. So this will be Ax plus B. So phi of X is equal to Ax plus B. So these two conditions are satisfied, and this is a ring homomorphism. So you can easily check that this is a ring homomorphism. So this is in terms of existence. But we also need to prove that this is unique. So let's try to prove that this is a this is a unique ring homomorphism we can get satisfying these three properties. Okay, let phi dash, let's say phi dash be another ring homomorphism from Rx to Rx, be a ring homomorphism. Now we don't know what it does on other elements, but we know that phi dash of R is equal to R for all R belongs to R, and phi dash of X is equal to Ax plus B. So we just considered that phi dash satisfies these two properties, and this is a ring homomorphism. And we have already our phi which we constructed. So we need to show that phi and phi dash are same. So what it means to say that phi and phi dash are same? What we should check?
They agree at every point.
Exactly. They should agree at every point. So phi is equal to phi dash to show phi is equal to phi dash that is phi of Rx, sorry, phi of fx. So if you take any x, this any polynomial fx, it should be same for all fx belongs to Rx. So yeah. Okay, so let's see. So fx represent the polynomial. Yeah. Now, okay, how shall we show that? So let's take. Let's just do it. So phi of fx. Okay. Okay. Tell me how should we do that? We should start with fx, right?
This phi prime will be completely determined once we know where we have to send the coefficients and x because of the properties of ring homomorphism.
Exactly. Yeah. Exactly. Because phi dash. Yeah. That's why this is unique. That is what we need to check, because uniqueness is in terms of, let's say, in this question. This says where it maps to the constant, where it maps to x. It's enough to get that information to find a ring homomorphism satisfying these two properties. Yeah, exactly. So right, so what should we do? We just take phi dash of fx And as we did, exactly, so as you said, we will split again, same thing as we did to construct it, where an is not equal to 0. Let's say this is fx. Then because of ring homomorphism, as I explained earlier, everything should split like this. Phi of an, phi of x raised to power n, and this will be equal to a0 because we know this information. Because of ring homomorphism, we get this equality. Yeah. So because of ring homomorphism, we get this equality. Now next, because of these two conditions, that it fixes every element of R, and phi of x is equal to ax plus b. Because of these two conditions, what we will get, a0 is plus a1 and ax plus b, an ax plus b raised to power n. So exactly what we constructed, and this will give us f of ax plus b, and that is equal to phi of x, phi of fx. And so we are done. Right? Anyone has any issue in this? You can ask. If you have any doubt, just let me know. So basically it says when we constructed, that was a unique construction. You cannot get anything else from here. So yeah, I don't know, Dinesh or who said that we can get it from these two information, like over x and over the constants. If we get the information, we will get the full and if we know that this is a ring homomorphism, we can get everything on the polynomials, on each polynomial. Okay, great. So let's see next part. So yeah, now what does this say? Determine the composite map FAB composition with FA dash B dash. So let's see what does so again, now now we know that this is a unique map, so let's define phi to be FAB. Let's write phi to be FAB. Okay, so now FAB over any element of Rx will be f of ax plus b. Now we know that this is a definition of the of the map FAB. So for all fx belongs to Rx. Okay. Right. So now let's see what does this say next. So let's fix some two more elements, a dash and b dash belongs to R. So these four elements we have. Fix these elements. Then it has been asked, what is FAB composition with FA dash B dash? So what is the meaning of composition? Usually what we will do, you have some map on, so this is your f, let's say. So any element x maps to fx. Now if you want to composite it with some other map g, then where does this map to? So f of x, you get whatever element you get, and then map fx to g of f of x. So this is the map, this is the composition we usually do. So same thing has been asked. So, and this is defined because domain and codomain are same. So FAB is a map from AX to BX, RX to RX, and also FA dash B dash is a map from RX to RX. Okay, so now what will be, I think, AB and A dash B, or other way around. Yeah, this is this composition with A dash B dash. So first we apply f a dash b dash, and then we will apply f a b. So this is the meaning of this composition. So f a dash b dash is so now where does will it will apply over elements of Rx. That means you consider any polynomial of Rx, then this will be f a comma b. Does this go? F a dash b dash. Now we have the defined notation. This notation means this for any AB. So we fix some element AB, or let's say XY or anything A dash B dash, and this map will map it to F A X plus B, or whatever A dash X plus B dash, whatever the elements are there. So what will be the map? F A dash Fx will be what? So this means this.
Yeah, of A dash X plus.
Exactly, yeah. So very good. So this will map to A dash X, sorry. So we have F also. So F of A dash X plus B dash. Right? So there are, yeah. Now f of AB, f A dash X plus B dash over this, how will it act? So this is again a polynomial. So you can think of this as some y. So f of y, let's say. Okay. So it's like f a b applied to f. So this is your new x, let's say. So f of y, I can. Okay. This is again a polynomial, or you can. Okay. Yeah. Right. So where does it will map? Again, like okay, should not write like this, can make confusion. So okay, so what do you think, where does this map to? So y could be a confusing notation, because we know what it does to y. We don't know what it does to y, or at least we should figure it out here.
Ma'am, we can substitute that yeah, Ax plus B in place of X again, so it will be done, I think.
Right? So what should I write here?
F of A dash bracket Ax plus B plus B dash.
Exactly. Yeah. Yeah, that y thing was wrong in my sense, of course. So yeah, exactly as you said. So what does this do? So if you say f a dash x plus b dash, this is like gx new, because this is a polynomial in x, so you will get some coefficients and other things when you expand it out, because you can expand it out, you can take the powers, use binomial expression, and write it in terms of x, powers of x. So this is like gx, and any element, this fab will map it to g of ax plus b. So what you can do in this place, you can just okay, yeah, write this as like here at the place of x, you can just write this ax plus b now. So a dash ax plus b plus b dash. So is this clear?
Yes, sir.
Okay. So this is this map. Now we can write it in the form of in our usual form. So a dash b plus b dash. So what I mean by usual form, this is an element of R. This is an element of R. So in terms of cx plus d, I wrote it. So now what it will be in terms of a notation of this fab, notation of fab. I can write it to be a dash a comma a dash b plus b dash, right, of f of x. Is that okay? So what will it be? So this will be equal to f of a dash a x plus this constant, right? So exactly this is the definition of small f a dash small f a b. This definition I used and I wrote it in this form. Is that okay?
Yes, ma'am.
Okay, great. So this is true for all fx belongs to. I took any random fx, so I can say that this is arbitrary, and this is true for every fx belongs to rx. Okay, so this means we can say that in terms of, because this is unique, so there is no issue in and there will be no problem. We can say that this is equal to, so as a map, this composition is again again yeah, is again this kind of map. So this is a usual thing when you get something like, so you can take FAP, like the you can take the set of functions of this kind FAB, where AB belongs to R. You can take this collection and you can say this collection has under composition. So you take this set, let's say I'll lambda, okay, so lambda comma with composition. So this composition, this this satisfies this composition thing, and you can also check that this is sorry, not composition, this closure property, because when you take the composition, you again get something of this kind. You again get this kind of map. So this collection of ring homomorphism of the kind FAB, you get so under composition you can prove that this is, at least this satisfies closure property. Second, this will satisfy associative, you can check directly. And I highly doubt this is commutative. You can check also, like either f a dash comma b dash is same as f a comma b or not. So as an exercise you can try what kind of lambda comma composition forms what kind of either monoid, which kind of set it forms, like. So this is lambda comma, not a monoid group. You can check this. Of course this is I'm not sure. Let's say check this also. Is this form a abelian group? So you have a operation, you have a set, you can check these properties. So as an exercise you can try this. So that's why this question might, you say, like here. Okay, let's see. Now what is the next part? So you have this, so kind of disclosure property. Now further show that if A is a unit in R, then FA is an isomorphism, and find its inverse. So first show that this if A is a unit in R, then FAV is an isomorphism. So for isomorphism, what you should know?
Kernel should be 0.
Sorry?
Kernel should be 0. Kernel.
Yeah, exactly, kernel should be 0. So also one more thing, when you say kernel, first we so exactly, this is a ring homomorphism, so it makes sense to say that this is a kernel. So yeah, because in the normal map, let's say a map from A to B, we say that if f of A is equal to 0, so in terms of kernel, what we say, all those elements of A such that f of A is equal to 0, this is a kernel of f, right? So, yeah, so this is the kernel of f, and although A belongs to B such that f of A is equal to 0, but so you should make sure that fa is equal to fa dash is like, so what I mean to say, like the property such that fa is equal to fa dash is similar to saying that for some element this is like this. So what I mean to say, for this it should be 0. So so for injectivity, what you need, f of a to b should be what? For injectivity, what you will check, there is no two elements which map to the same element, right? Two distinct element which map to the same element. So what you want to make sure that if f a dash is equal, f a is equal to f a dash, then this implies a is equal to a dash. This is injectivity, right? Now if you say kernel, you kernel is this property. So you so what you are saying, if f a is equal to f a dash, then this implies f of, if this condition holds, then this is similar, this property is similar to asking whether this a belongs to a, f a is equal to 0 is just 0, like only the 0 element maps to this, right? So here it will be okay, because this is a ring homomorphism. Because in this, if you have such kind of property, then you can write it like this, because of this f of a plus b is equal to f a plus f b. So yeah, you were right. You can try to do for the kernel, you can try to find the kernel. Okay, is that clear what I mean to say? Okay, I hope so. So I just want to say that first we should make sure that this is a ring homomorphism, then only we can talk about kernel, and we can check if kernel is 0, then this is injective. Of course, in our scenario this is a ring homomorphism, so we can of course apply this kernel thing, right? So or I can just go with the basic condition also. So I'll just go with this. So injectivity. So to check if f is a, so this is our map, f a b from rx to rx, which maps any element fx to f ax plus b. This is our map. So we need to show that if a is invertible. So what it mean to say a is a unit, a is a unit in R. So what does this mean? A has an inverse, so there exist, yeah, there exists some b belongs to Rx. So okay, this is a yeah, A is a unit in R. Although you can also verify that this was also in the lectures. Units of Rx is same as units of R. So you can also check this thing. Not exercise, maybe verify. Now this was in the lecture notes, so I can skip. So yeah, so it says if A is a unit in R, what does this mean? There exists some element B in R such that AB is equal to BA is equal to 1. 1 is that multiplicative identity of R. Multiplicative identity of R and Rx are same, because in terms of polynomial, as we said, this is 1. Okay, so let's see. So you have these two conditions. So you have FAB and A is a unit in R. So I'll just denote this inverse to be, because B is confusing, so maybe I should use some other element. Let's say C, and this is AC. And I can write C to be, I can define it to be, or this is the usual notation. This is equal to A inverse. C is equal to A inverse. Okay, so let's prove the injectivity. So let fx and gx belongs to R be such that f a comma b of fx is equal to f a comma b. Yes. So we need to make sure that fx is equal to gx to prove the injectivity. So we know that what does this mean? This is ax plus b. This is g ax plus b. Okay. So what should we do? Can anyone tell me? So what we need to prove that we have this condition for all x, or for all the type of thing like ax plus b is equal to for this kind of elements, this you have. Now you need to show that, to show from this condition that fx is equal to gx. So what should we do? Can anyone tell me? As an example, I can tell you that this is not always true, because let's say if a is equal to 0, then fb is equal to gb, like over constants these are equal. Anyway, we know that sorry, if it is equal on constant, that does not imply that fx is equal to gx, because you can take, for example, you have over constants this, then you can, what you can do, as you have defined in the beginning, that how shall I say, so for example, if fb is okay, let's say, so you have this map, so uh, this I mean, you take any f, any polynomial f and any polynomial g. If it is same at ax plus b, like f ax plus b is same as g ax plus b, then it does not mean always that fx is equal to gx. So for example, if fb is equal to gb, then this does not imply that fx is equal to gx. So you can take fx to be what, some polynomial with the constant coefficient is same, but you take any other, let's say dx, and gx is equal to uh, yeah, okay, dx, and this is b, or actually I can write minus x and plus x. So you take these two, fx and gx, then fb is equal to gb. Am I saying right? No. Okay, so okay, because if you apply b and b, then it will be like b minus x and b plus x, it will give okay, can you give me an example? Of course this is not true, so and this is only for b belongs to r. Oh, right. So b is a fixed element. B is not a variable, right? B is something fixed. So that also we need to make sure. We need to observe that. Let's say f1 is equal to g1. That does not imply I can take b to be 1 and a to be 0, because these are something we are choosing. And this does not imply f of x is equal to g of x. That you can make sure. So I can take example. Can you give me an example for such a thing? Hmm. So yeah, let's say this. Yeah, then if you take x equals to 1, then these two polynomials are same. These two polynomials satisfy that gf1 is equal to g1, so fx is equal to 1, and g1, so f1 is equal to 1 and g1 is also equal to 1, but this does not imply fx is equal to gx. Is that clear? Is that clear? I can repeat if you need. uh, you may say yes or no, maybe.
It's clear.
Yeah, okay, great. So right, so we know, so what I mean to say, that here you really need to use this property that a is invertible, a is a unit in r. So this does not always imply that fx is equal to gx. So can anyone give me a proof for this?
Ma'am,
Yeah.
actually we have to prove that kernel equal to 0. So if you take any polynomial other than 0,
You're right.
it should not be mapped to 0. That's it.
Exactly. Yeah, but this is same as this thing also. It's not
Yeah,
different.
because it is the highest. If you consider highest power, it should be some constant into unit.
Okay, so let's see. You want this, right? F(ax) plus b is equal to 0. So you want this set. You have all those f. You need to find all those fx belongs to rx such that f of ax plus b is equal to 0. Yeah, tell me. Now
If you consider highest coefficient in the resulting polynomial, that would be some constant into some few units. That would be never equal to 0 because a into some unit equal to 0 means if you multiply with unit again means the corresponding inverse, you have to get back the original constant. So it would be never it would never become 0. So that's why the only zero polynomial maps to 0. So kernel is 0. So that's it.
Yeah. So where did you use invertibility? I'm saying. So
suppose
yeah, you take this.
A into some unit equal to 0 means A equal to 0.
A into unit
equal to 0 means A equal to 0.
Exactly.
Okay. Suppose f of x is a given polynomial. So the resulting polynomial f of ax plus b.
Yeah, right. Then
so highest power in that one is some constant into some power of a.
Some so highest power, right? Yeah.
Highest power.
Exactly. So you say this is the highest power.
Highest power. So that would be an into a to the power of n.
Right. So
that would never become 0. So it means kernel is 0 only.
Right.
So that's it. It is an isomorphism. That's it.
Yeah, you are right. So that's what I am saying. Like you have to use A is invertible, and exactly you said that a raised to power n is not equal to 0 if this. Also note that if A is so A is not just unit. If you just say Rx is an integral domain, then also you can say that. Of course, I'm saying. Yeah.
Yes.
Exactly. So as you give this explanation, this is correct. So what he is saying, if you take so you can write it properly if you want. So you take fx belongs to Rx such that f(ax) plus b. So this is your kernel of f(ab). So this is equal to this. Then you want all those elements such that this happens. Now what he mean that if you take f(ax) plus b, then this is some kind of polynomial of the form ax plus b up to and so on an ax plus b raised to power n. And you want this to be 0. That means you can argue at least at this point, because if f is a non-constant polynomial, if n is or you can just say so this is equal to 0, then highest degree term, so the coefficient of x raised to power n, this has to be 0. So coefficient of x raised to power n is a raised to power n. So you will get, since this is equal to 0, of course, because this value is equal to 0, that means this coefficient of x raised to power n in this polynomial, that will be the coefficient, right? So this will be 0. That means, and you have, let's say n is n is bigger than or equal to 1, that means f is not a f is a non-constant polynomial, then and you know that a is invertible, that means you can multiply by, let's say, a inverse raised to power n, and you can get this to be 0, and this is invertible basically, so you get an is equal to 0. So if an is equal to 0, you can again argue, and you started with an is not equal to 0, because we always write f is a polynomial, like the highest degree term is non-zero, and yeah, an is equal to 0, so that means you cannot get this thing if you have a non-constant polynomial. For non-constant polynomial of polynomial f,
Non-zero polynomial. Yes.
no, right now non-constant, because I assumed n to be greater than or equal to 0, because here the argument works if n is not equal, yeah, n is, also you can include this. If n is equal to 0, then you will just get an, then an has to be 0, again a contradiction. So yeah, you can combine these two things, of course. So you get for all the, so basically for non-constant polynomials an has to be 0, and for also constant polynomials an, yeah, that's why I'm saying I should write it as a different. So n is greater than or equal to 1, and you have an is equal to 0, you get this. So for non-constant you get this, and for constant you already know, if it is a constant polynomial, whatever, let's say this could be anything, let's say a0, because it's just the constant one. So a0, that has to be 0, that means you are saying the constant has to be 0. So this really means that this is equal to the 0 side. So this is okay. Right, this explanation is fairly okay. Is that clear for everyone?
Yes, ma'am.
Yeah, I can give another argument also, because I already really need that. So so this is one way. Also, what you can do, a is invertible, so just think about it. If you have this thing, you have actually worked over, you know that what the composition of two functions are. So what you can do here, only you can multiply by, so what I really need, so in the normal situation when you need to show that this is a polynomial, and so you really need to choose x to be something such that you can get fx is equal to gx. So what I really mean to say, that you pick, so I'll write here, so you have injectivity thing, and you have fab of fx is equal to fab of gx, and you got fax plus b is equal to gx plus b, gax plus b. So what you can really think, that you choose some x such that you get fx is equal to gx. So what I can do, I multiply, so I need to remove, I need to get rid of a, so I can multiply by a inverse. Okay, I'm choosing x to be such that, so a inverse, something of that kind. And what I can do, so okay, so what I'm saying, okay, I'll just write here. So and also I want to get rid of this b, so this will make sure that a will be gone, and here also you multiply by a, you will get minus b, and this will get rid of a. So what I'm really doing, so you have fab, you compose it with a inverse, and I'm picking it to be minus b by a. By a means a inverse again, so it's not really different. So you multiply by this, and you can actually get what you really need, because a is invertible, I can do that. This a inverse are defined. A is invertible in R, that means A inverse belongs to R. So this property I'm using, and this product is there, minus B is always there because this is a abelian group with respect to addition. And you do this FAB, F of, so this is Gx. So as you have seen in the earlier part, this will give what? This will give F A dash A plus A dash B plus B, right? So yeah, oh yeah, it's fine. Okay, so you have this property. So what will you get? You will get A inverse A and A dash A dash B means A here, A dash B means this one. So you have minus B A inverse plus B, and both side you will get this. I will I can of course prove injectivity without saying these things, but anyway somehow you are doing it in your mind. So this is like, this is F of A inverse A is just identity 1, and this is what A inverse will be just identity. This will be minus B plus B, this is 0. So I'll explain why I did this. So this is Gx. And what does this do? F of Ax plus B, this is A, this is B, so you will just get 1 into x plus 0, and both side you will get this. So you really get fx is equal to Gx. But now this one really working, this is giving me everything: injectivity, surjectivity, and even the inverse. So I'm saying this is the inverse of your inverse of f a comma b, because when I apply this, then you get the what is happening when you apply this on FAB, you get fx. So what is the inverse of FAB? You multiply with this, you get the same thing, right? You take the composition of both, you will get the element which you started with, right? So this is the inverse of FAB. So the requirement in the question is done in that sense that FAB is an isomorphism. You can now prove that this is an isomorphism and find its inverse. This is the inverse. Okay. So for surjectivity, I can write. So you take Gx surjectivity. This is Gx. You take Gx belongs to Rx. Then f of, then what you really need? You need the inverse of Gx. So inverse of Gx means you take, so the as I said, the good choice is this element A inverse minus B inverse. So what I mean to say that, so you want FAB, when you apply on this you get Gx. So what you can choose, you take A inverse X plus A inverse B. I wrote, yeah, A inverse minus B.
Ma'am, you missed B dash, not B, that one.
Sorry?
That is B dash, ma'am.
Where exactly? Here?
That A dash B, A dash B plus B dash, I think.
Oh, there. Let me check.
There only.
Yeah, this is A dash B plus B. Oh, this is B dash. Okay, right. Yeah. Thank you. Of course, it should involve. Yeah, B dash. Yeah, here B dash, and oh, not B dash. B dash means, yeah, B dash is this one, and the inside one is this only. So yeah, we are good here. Yeah. Yeah, thank you. So you take g of A inverse x plus A minus A inverse B. So if you take this and you apply FAB, then you will get gx. So what I just did, I just took this inverse the uh, and wrote it in this form, and I got it because this is some polynomial hx, and I gave a pre-image. Is that clear? And as I said, this will work the inverse of FAB. Is that okay?
Okay, ma'am.
Okay, great. So the exercise which I gave earlier, this one, so you can really see when A is invertible, then it might form a group because you have inverses, so you can think about it. Okay, I'll the notes I will write it anyway properly and upload in the Google Drive, so you can access from there maybe by tomorrow or tonight if possible. Okay, so let's see this question next.
Hello.
Yeah.
Uh,
Hmm.
Ma'am, if I define
Hmm.
the image of x, some quadratic polynomial.
Okay. Here in this previous question.
Yes, yes.
Okay.
So
Image
instead of AB,
Hmm.
there will be three constants, say A, B, C.
Okay. Yeah.
So such a map exists by universal property of polynomial rings
Okay. Yeah. Of
because
course. Mm-hmm.
on constants it's equal, so we can extend it.
Yeah. So
So
yeah.
is this imply that set of all,
Mm-hmm.
these are the only isomorphisms
No.
in
No. So
polynomial rings?
no.
Because
No.
the
No. Wait. Quadratics are. Okay.
if I define image
Mm-hmm.
of x any polynomial,
Mm-hmm.
then such a map exists.
Right. Right.
So the uniqueness part is done, that there exists a unique homomorphism, and composition also follows.
Yeah, uniqueness. I'm not sure. How will you say uniqueness?
So the universal property of polynomial ring says if we have a map
Mm-hmm.
from a ring R to suppose R is our ring and Rx is S. So R to Rx we have this constant map.
Mm-hmm.
Then
You can
once I
extend.
define the image of X, then there exists a unique ring homomorphism from Rx to Rx such that the following diagram just commutes.
Right.
Means
Right.
like
Right. Right.
so
So you
so
have.
such a map
Mm-hmm.
so such a map exists and that is unique.
Right.
Now,
Right. Mm-hmm.
but the question is,
Mm-hmm.
it says, is this map a isomorphism or not? So then the subjectivity part, when we define it's not subjective, right? So is this imply that the set of all isomorphisms from Rx to Rx has to be of this form, that Ax plus B? Means they inject.
Mm-hmm. Actually, it will be, yeah, it will be because if you take any degree, let's say if A is non-zero and you define it to be like this, then any polynomial you will take, the degree will increase only. So you cannot get degree 1 in the right part. So as a image you cannot get degree 1 polynomial. So let's say the inverse, the what element will you take if you want it to map it to x? You cannot take anything.
Yes,
because,
agreed.
yeah.
Agreed, ma'am. So does this imply that set of all isomorphisms, and means these are the only isomorphisms from Rx to Rx? Because degree 2, we cannot map x to some degree 2 polynomial.
Right.
We have to map some Ax plus B.
Yeah, you are
So
right. Yeah.
so whenever there is isomorphism between Rx to Rx, there has to be of this form.
Exactly.
Is this right, ma'am?
Yeah.
Yeah.
It will be of this form, of course.
Okay. Thank
Yeah.
you.
Yeah. Yeah. Nice observation. Yeah. Yeah. Great. So yeah. Let's say this question. K be a field, and A B belongs to K, and A is not equal to 0, Then with the notation as in exercise 1.1 above, show that degree of, okay, so you have given A is not equal to 0 and K is a field. So what is a field? Now with ring, you have the property of inverse of multiplication. So with respect to K plus, it is abelian group. K dot is also abelian group. And these two operations are related with the distributive property. So you have these 11 properties if you count. Okay, so distributive property of multiplication over addition. So A dot B plus C is equal to A dot B plus A dot C. So you have all these properties. So what does this mean? K dot is an abelian group. I should write K star. K star means with I have removed 0 because 0 does not have inverse in multiplication. So you remove that 0, and then K star dot should be an abelian group. Okay. So, can you tell me what does this mean that A is not equal to 0? So, in this scenario, it belongs to A is not equal to 0. This implies A belongs to K star. K cross. And yeah, K cross is better to say here. So, A belongs to K cross. Then so this implies and K cross dot is an abelian group. That means A is invertible. A is a unit in K. Unit means this is invertible. So all the so in the field all the non-zero elements are units in K. Okay. So let's see this first part. So it says degree of f a comma b fx. Okay, one more thing I want to say. I'll just add this one. Yeah. So okay, just think about if you have zx to zx and you map. So as an example I'm giving, if you take FAB, then and x maps to ax plus b, and let's say a is 2, or just you just take x maps to 2x, then is this map surjective, injective? Can you tell me about anything here? So the map is defined to be, I'll just write FAB. This is a ring homomorphism first. These three conditions we need as we have observed. This is a ring homomorphism.
Ma'am, it is injective, not surjective.
Exactly. Yeah. So C belongs to R and FAB and X maps to 2X. So yeah, as you said, this is an injective map because if for injectivity you just need integral domain, and Z is an integral domain, and so is ZX. So injectivity is okay, and for surjectivity this is a problem because you cannot find inverse of x. And why this is happening? Because 2 is not invertible. 2 is not invertible in ZX. So 2 is not invertible in Z, at least, or ZX you can say, because units are same in Z and ZX. So surjectivity is not following here. Okay, so I just wanted to give an example, so you can try the examples and you can observe that what FAB is doing. Okay, for different rings you can try. Okay, so this was one example. So really we need A is invertible. So let's see this this question. Degree of FAB fx is equal to degree of fx for every f belongs to kx. You need to prove this. So what does this mean, degree of FABX, AB of fx? what does this mean? I'll write again fx to be in the form of, okay, firstly I can write this as ax plus b, fax plus b, and then I can write this to be, yeah, the earlier argument will work again of injectivity. I think, sorry, yeah, ax plus b raised to power n, and an is not equal to 0. So degree, if you want to find the degree, what you need to see, what is the highest power of x appearing with non-zero coefficient. So here you can see you have x raised to power n, highest power, but we don't know if highest power in the sense that x raised to power n is there, but we don't know if the coefficient is 0 or non-zero. So we can see what is the coefficient, an a raised to power n. So this earlier argument of injectivity will work here. Yeah, that is nice. So an a raised to power n, x raised to power n. So this coefficient you need to check if this is 0 or non-zero. So now it is given that a is not equal to 0. So a is a unit in k, or a is at least like, so an a raised to power n, this you need to check if this is 0. So you know that a is not equal to 0, so a raised to power n will be not equal to 0, because this is an integral domain, or you can use the unit property. Unit is bigger, actually. You can directly just use integral domain. Integral domain means if ab is not equal to 0, this implies a is not equal to 0 and b is not equal to sorry, yeah, I wrote it wrong. So if you have ab, if you have a is not equal to 0 and b is not equal to 0, this implies ab is not equal to 0. So this is integral domain. Since a is not equal to 0, so a into a, this all the product will be non-zero. And you know that you started with f with an is not equal to 0. So again this product with two non-zero, multiplying two non-zero elements, this will be non-zero, because you are in an integral domain. Field is always an integral domain. Okay, so degree of this will be what? I should not write here degree. So degree of fa comma b fx will be what? N. So a is not equal to 0 is making sure that degree will stay same in this map. Okay, is this clear? If not, just let me know. Is this clear?
Yes, ma'am.
Okay, great. So let's see the second part. If f belongs to kx is irreducible over k, then so is fabfx. So you have again the same thing. A is not equal to 0, so it's like this is invertible. Now f is an irreducible. So irreducible means irreducible element of a ring. Now ring is Rx right now, means for any ring, so I can write for S if you want. Irreducible element of a ring S means there does not so this implies if fx is okay, if you okay, I'm writing in Rx only right now. So irreducible element means if you write fx to be as gx into hx, and then one of them has to be, yeah, so one of them has to be a unit. So either gx or hx has to be a unit. Fx is irreducible implies, means either this or this is a unit, in that ring, unit in Rx. So now units in Rx are constants. Constants means elements of Rx. So what you can really say that Gx and Hx, degree of Gx is equal to 0 and degree of Hx is equal to 0. Okay, 0 is not a unit, and degree of 0 is minus infinity to define. Okay, so you have this scenario. So this means this here in Rx, because you know that units in Rx are really units of R. Okay, so uh, you have been asked f is irreducible, f belongs to kx is irreducible but in k, it is given that, given. And to check fab of fx is irreducible or not, that is your question, is irreducible. Okay, this is again in k, because if you change the field it could be different, like in the field. So for example, x square plus 1 is irreducible in real number set, but x square plus 1 is not irreducible in complex numbers. So if you extend the field, you can this property could be changed. So you need to check whether this is irreducible or not. So let's say, so basically not check, to show this is irreducible. So let's see, fab fx is so let's say this is not irreducible. Let's say this is not irreducible, or this is reducible in k. What does this mean? This implies fab fx is equal to some gx into hx. So I'm writing in the sense that because both domain and codomain are same, so you can be confused here. So I'm just saying you have some polynomial. This polynomial can be written into reduced form. So you have gx and hx with degree of gx is greater than 1, not greater than or equal to 1, because if it is 0 then it is a constant and this is a unit because you are in field. So degree of hx is greater than 1. So you have these two properties. Let's say this is reducible, and now what does this mean? This implies now you know that if since a is not equal to 0, and you know that if a is not equal to 0 from first question, that you have this map A inverse. So you have an isomorphism and you have an inverse of fab, like of the function of the map. So you have this minus b A inverse. If you apply this here, you can do that because it's just a map. So you just apply it here. What will you get? You will get fa inverse comma minus b A inverse. Oh, there are too many. Yeah. Of g of x into h of x, right? And now you know that this map is what? This is a ring homomorphism. And on the left side, what will you get? F of ax plus b. You will get f of x, right? As you know that this is these are inverses to each other, you will just get fx. And on the right side, what will you get? You apply this to gx and hx. So you will get g of a inverse x minus b A inverse into h of a inverse x minus b A inverse. So what you these are some polynomials. Let's say new name, you can say g1x and you can say h1x, because you can expand it out. You can write it in the form of the variable x, right? So so what you really got, fx is equal to g1x into h1x. Also you now this will give a contradiction if you can make sure that the degrees of these are bigger. Degrees of these are bigger than or equal to 1, then only you can say that this can give a contradiction. So what I really mean to give a contradiction, I have assumed that this is reducible. I want to show that if you assume this, then f has to be reducible. So, and you got something of this kind, fx is equal to g1x into h1x. So you got this factors, but now what you need to make sure that this g1x and h1x are not units. So what does this mean? You want to make sure that this. So this is a question. So can you tell me if these are the degrees? You can say that degrees are bigger than or equal to 1. You have this much information and you applied f on gx and hx. So can you tell me, can this make sure that the resultant, so basically what you have, f a inverse minus b a inverse of gx is equal to g1x. Now think about this in the sense of first question, first part, degree of this part. You know that if degree of fax, now at the place of a I have a inverse, and a inverse is again non-zero because a is non-zero, so a inverse is non-zero. So degree of this will be same as degree of fx. Is that okay? So I'm using this property. I'm saying that so degree will be the same, and hence degree will be like greater than or equal to 1. Is that argument clear?
Yes, ma'am.
Okay, great. So you have this. So what I did, just we can walk through this. So you assume that this is fab of fx is reducible, and you write it in the form of gx into hx, and you apply the inverse, and apply the inverse from the first question, because you know that a is non-zero, so a is a unit. So you can apply the inverse, and when you apply the inverse, you get some equation over fx. You get factors of fx, and then from the second of first, you got that the degrees will be the same. So you get degree of g1 and degree of h1 to be greater than or equal to 1, this new factors, and which means fx is reducible, which is a contradiction, reducible in k or kx. This is a contradiction, and you are done. Okay, so I hope this is clear. If not, just let me know, like I can explain again. Okay, so let's see. Yeah.
If it is, if it is not isomorphism and just a surjective map, will this proof work?
Just a surjective map. Okay. What does this mean to have surjective map? You have inverse of everything. So inverse of inverse. So first think of an example which is not injective and surjective. Can you find such a map? Think about it. So one example I gave, which is injective but not surjective. So okay, question.
Ma'am,
Yeah.
inverse exist means it is bijective, ma'am.
Yeah, inverse exist means it is a bijective map, but
Bijective, yes.
yeah. So can you, so as he asked, can you find an example of FAB such that, find some FAB such that FAB is surjective but not injective? This might be hard because I don't think such an example exists, but you can try it out. And on the top of my head, I think this cannot be a case, because surjectivity means degrees has to be constant first, because surjectivity, for every element you should find the inverse. So but when you start with x, you are defining a map on x, so you really have to keep it linear first. And when you keep it linear, you have just two choices, either like ax plus b, and you can have a to be invertible or not, and that will make sure, that will only cover the injectivity part. So I think, because why I'm saying this has to be this has to map a linear one, because as you said, if it is quadratic or cubic, then degrees will increase. You can never get inverse of x here. So to make sure that you have the inverse, you have to map it to a linear map, and then you can so my perception is, I think this won't exist, but you can try as an example. Like, you can try, you start with a linear map, and then I think you just land up with if a is invertible or not. So yeah, that will be a good exercise to do.
I just wanted to check that in the proofs, what exact properties we have
Right.
mentioned.
So we only used a is invertible. We used this property because, I have multiplied with this term, and that I am getting because a is invertible. So that property I used here. Yeah. Surjectivity. Yeah. Even. So what you can do? You can try in this example also. Is this true or not? So, for example, for example, see this. In this property, this does not work because you started with x. That is irreducible, but 2x is not irreducible. It maps to 2x, which is not which is reducible, I mean, because 2 is not a unit and x is also not a unit. So you got 2x, and that is reducible. So reducible means you can write it in some factors of non-unit factors, and x is a non-unit at 2 is a non-unit in z. 2 1 by 2 does not exist here, so 2 is not a unit. So this 2x is reducible, but x is not reducible. So this is a counter example, at least for, so a is invert. So that's why I'm saying a is invertible is required here. That is the only thing I think you require. And actually, if a is invertible, you are getting isomorphism just by this property. Is that clear?
So yes.
Yeah.
So what are the like analog of if we increase
Hmm.
like if I sin x to x square or quadratic or some other polynomial, then is there any analog for this? Like if it is reducible and it's surjective or something injective, because there might not there are no isomorphisms. Isomorphism has to be of these forms. So if f is irreducible here, then after transforming, is it remain like what kind of transformation
I think.
maintain this
I think.
irreducibility criteria?
So you can try one thing at least, but so if x maps to a irreducible element, irreducible degree, let's say irreducible polynomial, because so like in the next question, the irreducibles of higher degree are there. So if you map it to irreducible element, you can at least try that whether this is you can get this kind of condition or not. You started with an irreducible element and you mapped it to a reducible element. Will this make sure for every element? Like, will this make sure for every fx you can get something of like this will be reducible? And so you can try this out. I also have to try. I cannot say just looking at that this will be true or not, but that could be a good example to try. Like, you take x maps to a reducible polynomial, and then you check whether every irreducible maps to a reducible. That could be an option to try. I'll try and maybe write in the notes. Like, I'll share these notes with well written thing. So maybe I'll try to write if I can. Uh, is that okay?
Yes.
Okay. Yeah. Okay. Let's see this next question. You can also try and let me know in the next class, maybe. Yeah. I'll be happy to listen. Okay, so let p be greater than 0, and this is a prime number. You have been asked, and you have this polynomial a n x is to power. You are in integer ring, so you have ring of integers, and you know that p does not divide an, and you take f bar. F bar is what? You take a0 bar plus a1 bar an bar x raised to power n. This belongs to zpx, where these ai's are ai modulo p. So whatever you have, for example, you have 5, you go modulo, let's say p is 2, then you get just 1. So you know this modulo. So this is also a ring, and you can check that zp is a field, because if p is prime, then zp is a field. That is, you can check. And this is ring of integers. This is zpx. Are you familiar with these notations? These are in the lecture notes. I can explain if you want. Just let me know if I should. Okay, just let me know if I can explain the definitions. I can write the definitions here. Okay, so f bar is this, and you have f with a condition that p does not divide an. So this question is related to this what do we say, prime number test or something, prime root test. Okay, so I'll come here. So what you have been asked that show that if f bar is irreducible in zpx, then f is irreducible in zx. So in field theory, you to find irreducibles is a major task. Like you even don't know what are all the irreducibles in bigger rings. That is also a big question, big research problem. So basically you need to find all the irreducibles in zx. Okay, so it says that if f bar is irreducible in zpx, like if you can find just one prime such that f bar is irreducible in zpx, then you can say that f is irreducible in zx. So that is a very good property. So what you can do, if you are in zx, you can just you can just go modulo with some z prime, let's say z2 or z3. You can check on just one prime, and if that is irreducible there, you can say that this is irreducible in zx. So that is a very good property. So let's prove this first, and then we can try this we can use this property to check that whether these 5 polynomials are irreducible or not. So given that f bar is irreducible, okay, f bar is irreducible in z px, so there is some fixed p for which this is happening, and p does not divide an. Okay, and you need to show that f is irreducible in zx. Okay, so let's say this is not, of course, that is a best way to do. F is reducible. Let's say, suppose f is reducible in zx. What does that mean? You get some gx hx in zx such that degree of gx is greater than or equal to 1, and degree of hx is greater than or equal to 1. Okay, so one more thing, I should not say that because there are units which are also not reducible. So let's see if we need this condition or not. We can see that later. What I mean to say, because 2 into x is reducible, and 2 is a constant. So what I mean, units, there are non-units in z, right? Because units of z are just plus minus 1. Okay, So actually I should not say this. It could be 0. Okay. Okay, let's see how this goes. So fx is equal to gx into hx. Now you apply, you just do mod p. What will you get? So gx into hx. Now one property, you know, a dot b in any ring, a dot b is equal to ab mod p, or maybe I can write ab. If you can see this in z, you can actually prove that this is true in gx, like in zx also. So what you will do, you take gx, you take hx, you multiply it, then you will get coefficients, and then over coefficients it will split. So over coefficients you will get something like a1 into b1 bar, and then that can be splitted as a1 bar into b1 bar, and then you can get, what I mean to say, you can really get here gx bar into hx bar. Okay. Now what does this mean? This means that you have some factors over mod p. Okay. So over mod p, now one more thing, gx and hx you have, you must be having something like, so yeah, so gx is something, okay, how shall I say, so you take leading coefficient of gx, that has to be non-zero, and leading coefficient of hx, that has to be non-zero. Leading coefficient means the highest degree term, so either it could be constant also, so you are saying that is non-zero. Okay, so leading coefficient is non-zero. So you have this property with gx and hx. So you need, so when you go mod this mod p, so over fx, mod p means you have like a0 plus a1x, so I can remove this for now. So you have fx is given to be a0 plus a1x an x raised to power n. You have this condition, and you know that p does not divide an. So you take leading coefficient of, let's say this coefficient is equal to I'm saying bm and ck, like, because the degrees might not be same. So bm and ck, so let's say these are the leading coefficient. What does this mean? And you are multiplying it and you are getting some degrees, right? So the coefficient gx into hx, the highest degree term, when you multiply it, you will get x raised to power n, right? So you will have something like bm into ck, and p does not divide that. That means p does not divide bm and p does not divide ck. So these are really irreducibles. So this gives so gx bar and hx bar gives a reduction of f bar x. So this implies f bar x is irreducible, and that's a contradiction, because you started with the, because you know that it is given that f bar is irreducible. Okay, so this property will make sure that f bar x, if f bar x is irreducible, then fx is irreducible. Okay, so let's use this property in these examples. So you have x cube plus x okay, I'll just copy this. So you have this, and let's say for this, you have x cube minus x plus 1. Take this example. So what will you have? Now if you can prove that this is non-zero, this is irreducible over some zpx, then this will be irreducible in zx. So can you tell me if this is what p can you take here?
P is equal to 2.
Okay, exactly. So you take p equals to 2. That means you are going modulo, you are going in z2x. Exactly. So you have, it's like x cube plus x plus 1. What does this mean? It is irreducible. You have to prove that this is irreducible in z2x. So how will you prove that this is irreducible in z2x?
There are no roots in Z2x. Because it is a cubic polynomial.
Hmm.
For it to be reducible, it must have root.
Exactly. So this is a cubic polynomial. If it has to factor, then it will be it will has to be linear into quadratic, right? What possibility you can have? This is 3 degrees, so either linear into quadratic. Okay. Because this is monic. One more thing, this is an important thing, because this is monic. There is no coefficient, so you cannot have something like 2 into x. This kind of thing is not there, so you cannot really write 2 into some polynomial. Okay, so constant term is gone, so you cannot take factor to be a constant one. So you have only choices to be linear and linear into quadratic. Now linear means there is some root, because linear will be of the kind x minus b. So x plus b or x minus b, because this is monic, the constant term, and you are in integral domain, so degree will increase. So you are getting 1 to be into something a into b, then a into b has to be something like oh, and you are in z2, so don't worry about that. I can ignore this fact. So you have x minus b. So that means there is some root. There is some root of z. There is some root of this in z2, right? That means when you apply 1 0 or this, then you will get something like that. So let's check. So if I say this to be fx, then this will be equal to I have wrote minus 1 to be plus 1, because in z2 you have just two elements, 0 and 1, and minus of 1 is just 1. So so f of x is so when you evaluate this at 0, you will get 1. When you evaluate it at 1, you will get 1 again, right? Because 1 plus 1 plus 1, that is 0, plus 1, that is 1. Okay. So there is you will not have any linear factor, because if there is a linear factor, there has to be some root in f2, in z2, right? So 0 and 1 is not satisfying, so you don't have any factor, linear factor, and that's why this is irreducible. This implies this is irreducible in z2, and you are done. Irreducible in z2, this implies irreducible in z, because of the property we proved. Okay, let's take another one, x cube plus 2x plus 1. So what can you take as an example here? Like which p you can take?
So p is equal to 3.
P equals to 3. Okay, so if you take p equals to 3, what will you get? So yeah, again the same thing, linear into quadratic. There is only one possibility, because this is 3 degrees, so linear plus quadratic will give 3. So p equals to 3. Let's try it out. So if I say this to be fx, you will get f of 0 is equal to what? 1. F of 1 is equal to 1 plus 2 plus 1, that is again 1, because 1 plus 2 is 3, and like 4 modulo 3, that is 1. So this we are working in mod right now, so no issues. And let's take f2, then what will you get? 1 plus 2 into 2, oh sorry, 2 cube plus 2 into 2 plus 1, you get 8 plus 4 plus 1, that is 13. And if you go modulo 3, this is definitely non-zero, you have 1 bar. Okay, so you tried all three, and all three are when you any of them is not a root. 0, 1 and 2 is not a root of f. So you have this condition that f of z, so this means this is irreducible. Same process. If you have any doubt, just let me know. Irreducible in Z3 implies irreducible in Zx. Is that okay? Because there is no root in Z3, and if cubic has to factor, it has to factor in linear and quadratic, because this is a monic polynomial. So, and linear factor means that there is some root of fx in the ring Z3x or Zpx, whichever we are taking. And if there is no root, then it cannot factor. So that is the property we are using here. Okay, let's see third one, x cube plus x minus 1. So we have to walk through from the, so let's try p2 first, p equals to 2. So when you take p equals to 2, yeah, so what will happen? So you will get 1 plus 1 minus 1. So, oh, yeah, p2 could be, yeah, p2 could work. Sorry, p equals to 2 could work or not for this one.
Ma'am, let's try x to the power of 5.
Sorry?
Can we try x to the power of 5x?
Yeah, okay.
This is same.
Okay. So let's try this out. X raised to power 5 minus x plus 1. Okay, so yeah, for this one also p equals to 2 could work. Okay, so let's try p raised to power 5 minus x plus 1. Now you have more problems, because it could factor in linear into some biquadratic or quartic, or it could factor in quadratic into cubic, right? So we can eliminate this case by checking that whether linear factor is there, so checking the roots. But the second part we have to be careful, because we cannot really get rid of this easily. Okay, so let's see, for x raised to power 5 minus x plus 1, so okay, so if you take p equals to 2, then you have this linear thing will like, when you take p equals to 2, you will get 0 minus 0 plus 1. So in p equals to 2, there is no root, so first one could get cancelled, but the other one could be a problem. Okay, so basically you need to check all the cases. So actually there is some maybe sir will discuss a property, but let's say, so you take p equals to 5. Okay, when you take p equals to 5,
Ma'am, I think we don't need to go to code for that one. If we try x square minus x plus 1 plus 1 or minus 1, that would be sufficient, I think.
for quadratic you are saying, no?
Yes, ma'am. Yes.
Actually this has factors, so you divide by this.
Plus or minus 1. Yeah. That would be done.
Yeah, that would be done. So you can check that this has factors directly. So for quadratic, so but at the first place you don't, sorry, x square I mean. So I can write it down, maybe 1 second. Yeah, so it factors in x cube plus x square minus 1, and you have x square minus x plus 1. So basically you need to try. As I said, this is not very easy to figure out every polynomial is irreducible or not. So you have to try many things. So for linear you try the roots, and for quadratic you have to try all the possibilities. So after 5 it's very hard to even check the things, because you have cubic into cubic also. So this is a problem. So you can check that this is true, x raised to power 5 minus x plus 1. You can be clever in the form that you can really split it out by some clever addition and subtraction. That could be one option, but you can check that this is true. Okay, so this is reducible. So this is a reducible case. So let's discuss the fifth one. Okay, So fifth one is x raised to power 5 minus x plus 1. So this minus is flipped. Oh, wait. I think I wrote off the wrong one. So this is minus 1 into plus 1.
I
So
think it's okay,
yeah,
man.
yeah, this
Okay, it's
is.
okay. Let's leave it there.
Sorry? No,
I
no,
think
no.
it's okay. Yeah.
Yeah, this is plus and minus 1. So this is different. This is, I'm claiming that this is reducible and this is reducible. So these are just minus and plus are flipped. So this is a different case. So I'll just tell you what trick you can use, because as I said, this is not so easy to figure out how exactly you can check. So you take x raised to power 5 minus x plus 1 and you go in f5. Okay. So in f5, can you tell me whether this has linear? So again, you have two options: linear into biquadratic, and yeah. So sorry, I wrote f5. Access Yatraj. Oh, okay. Sorry, I have muted Yatraj. So you have quadratic and you can take cubic. Okay, these two options are there. If there is linear factor, that means you have a root here, right? So that means if you take f of x, can you tell me if there is any root or not in Z5? So you will try 0, 1, 2,
No,
3, 4.
there cannot be root. There
Okay,
cannot be root.
exactly. There are no
X
roots.
plus
So
5,
yeah.
x plus 5 minus x is 0 for any x.
Yeah, exactly. So because x raised to power 5 minus x is equal to 0, because if you know, fields can be defined like this. So x raised to power 5 minus x will always be 0 in Z5. So you will always get 1. So this cannot have a root here. So this case is gone. So you need to just check quadratic into cubic. So sorry. So what you do, you take fx. So okay, take a function. So let's say phi from z5x to z5x. You can check this is a ring homomorphism, and where it maps phi of r is equal to r for all r belongs to z5, and phi of x maps to x plus 1. So it's like ax plus b map. So and a is invertible here because you can see that a is 1. So and you know that in z 1 is invertible because that is multiplicative identity. So you take this map. Okay, now in this map, if you take fx, then where it will go? It will map to x raised to power 5 minus, sorry, it will map to x plus 1 raised to power 5 minus x plus 1 plus 1. What will you get? Okay, so when you expand it, do you know x plus 1 raised to power 5 will be equal to x raised to power 5 plus 1, because x plus 1, when you expand it with binomial coefficients, so you will get something multiple of 5 into x raised to power 4, something multiple of 5 x raised to power 3, and so on with 1. So all the coefficients of x raised to power 4, x raised to power 3, x raised to power 4, 2 and 1 will be a multiple of 5. So and multiple of 5 means, and you are in mod 5 situation, so this will be 0, this will be 0. So you will just get x raised to power 5 plus 1. So this is a property that if you are in ZP, then x plus any x plus y raised to power that p will be same as x raised to power p plus y raised to power p. You can check that, just binomial expansion, nothing else. Okay, and here you will get x minus 1 plus 1, and you will get x raised to power 5 minus x, and 1 is 1 cancelled, so you get this, and that is same as fx. So what did you get? Phi of fx is same as phi of is same as fx. So it's like you have a map, and you have checked that if okay. So yeah, what I mean, So if phi of fx splits into, let's say, qx into rx, where this is a quadratic one and this is a cubic one, then this will be equal to qx into rx, right? I'm saying this splits, okay? Let's say it splits in quadratic into cubic, then phi of fx is same as fx, and this is a ring homomorphism as we have proved. So this will be equal to qx into rx, right? Now, what does this mean? Okay, one more thing. This is quadratic and cubic, and I'm saying this is irreducible. Can you tell me why these factors are irreducible? Just one line explanation. I'm saying if it splits in quadratic and cubic, then these factors has to be irreducible.
Because they have got no roots.
Exactly. So there are very good. So there are no roots of fx. So if it splits in quadratic and cubic, you cannot further split it because this will be linear factors again. Then you have a root. So these are irreducibles, and this is of course irreducible. This is irreducible. So I'm saying that phi of qx will have to map to qx because it fixes degree. As you have seen, when a is invertible, when a is non-zero, then in field, so a is invertible, so this means degree is fixed. So quadratic will map to a quadratic, cubic will map to a cubic. So when you do it, you can see that this is equal to this. So phi will map qx to qx, and phi of rx has to map to rx, okay? Because these are irreducible, so you cannot get some multiple or this kind of thing, okay? So, and degree is same, so degree fixed, phi fixes degree, okay? Now when you see this quadratic thing, phi of qx maps to qx, so you so what will be the claim? There is no quadratic polynomial in z5x. You have z5x. There is no quadratic in z5x which is fixed by phi. So you can actually prove that there is no quadratic in z5x where phi fixes that quadratic, okay? So what you can do, you can just take something like this, and do you want me to do that, or you can do it by yourself? So you are saying this is same, and you are in z5, so you can go mod 5, and you can say that this there cannot be something of this kind, okay? So I can keep it as an exercise, and this will contradict the fact that fx is so this implies fx, so this is a contradiction to fx is reducible, so fx is irreducible in z5x, okay? Is that clear? And this will apply in zx. Is that clear? Yes, Yatraj.
I just have one.
Tell me.
So could we have done it directly in z of x itself? Now, assuming that knowing that z of x is a unique factorization domain.
So how will you do it? You will again consider all the
Like-
factors, right? So what happens? Let me tell you. So what happens when you go so you can try, of course, this ax square plus bx plus c, and you take some cubic and do this. But when you go mod 5 or something like that, then the irreducibility count is very less. Like there are few irreducible polynomials existing there. Because when you go, for example, in z2, there is only in z2x, there is only one irreducible of degree 2. That is x square plus x plus 1. Just one
Oh, yeah.
irreducible.
Oh, yeah, yeah. I understood. I understood.
So
Sorry.
it's
So
like,
I,
yeah, yeah.
no, because we have gone to, Z5, that's why we have got f of x plus 1 is equal to f of x. So, okay, okay.
Yeah, yeah,
So
exactly.
I just got confused. Yeah.
Yes, yes,
I,
yes, yeah, you observed
thanks.
correctly. Yeah. So it helps in the, like, you are in a smaller ring, ZX is a big ring, so you are in a smaller ring, you can figure better
Yes,
things there.
yes,
So
yes.
yeah, but of course, this does not make sure. Like for reducibility, you cannot say. For example, also okay, you can also prove that of this kind, x raised to power 5 minus x plus r, you have some r here, r belongs to the ring Z, then you can prove that this is irreducible by the same argument for this r equals to one thing. This is one way. So what I mean earlier, so for example, if you take x square plus 1, then this is irreducible in z3x, because you have 0 1 2 does not satisfy this equation, so this is irreducible. But this is reducible in z5, because when you take 2 here, so x minus 2 is a factor here. X minus 2 divides x square plus 1, because when you take 2 here, 2 square plus 1 will be 5, that is mod 5 is 0. So you have a factor when you go mod z5. So I mean, if you say that it is irreducible in zpx, then you cannot say that this is irreducible in zqx for some other prime q. So this does not imply for different p's. So but if you can prove it for any of the ring, like for any of the zp, then you can say that it is irreducible in zx. That is a upshot of these questions. Is that clear? Okay. Okay, so these are all, of course I've taken too much time, but yeah. Yeah, this was the last question, so